In the last lesson, we met the Vigenère cipher and its proud nickname, the indecipherable cipher. For 3 centuries, that reputation held. In this one, we are going to watch it crumble, destroyed by 2 mathematicians working independently, almost a decade apart, with nothing more than pen, paper, and a single brilliant insight. The story of how Vigenère finally fell is, more than anything else, a story of 2 men. The first was Charles Babbage. Yes, the same Babbage who designed the first mechanical computer. Sometime around 1854, he quietly worked out the attack. And quietly is the operative word, because he never published it. The most likely explanation is that the British government had classified the technique as a military secret during the Crimean War, and Babbage was asked to keep it to himself. 9 years later, in 1863, a Prussian infantry officer named Friedrich Kasiski rediscovered the same attack from scratch, and unlike Babbage, he published it in a small book on military cryptography. So Babbage got there first, but Kasiski got the credit, and to this day the technique bears his name, the Kasiski examination. Before we get to the attack itself, there is one piece of vocabulary the whole technique hangs on. We need to talk about trigrams. A trigram is nothing more than a sequence of 3 consecutive letters. To see what that means in practice, take any word, say the word message. Now slide a 3-letter window across it. MES is a trigram. ESS is a trigram. SSA, SAG, AGE. 5 trigrams hidden inside a single 7-letter word. And here is why we care. In English, certain trigrams are wildly more common than others. V alone accounts for around 3% of every trigram you will ever read, and a small handful, and, ing, ion, ent, for, her, turn up almost everywhere you look. 3 letters, it turns out, is a sweet spot for an attacker. 2-letter diagrams are so common they tell you almost nothing. 4 letters or longer are so rare you almost never see a repeat. 3 is just right, and that Goldilocks property is exactly what Babbage and Kasiski were going to exploit. With trigrams in our pocket, we can state the central insight of the Kasiski attack, and to make it concrete, let us take a deliberately tiny example, the sentence, "Then I took the dog for a walk." One quick definition first. The period of a key is simply the number of letters it contains before it starts repeating itself. Our toy key here is KEY, 3 letters long, so its period is 3. Strip out the spaces, line up the letters, and notice something interesting. The trigram THE appears in this sentence twice, once at the start of the word then, at position 0, and again as the standalone word the, at position 9, 9 letters apart. Now lay the repeating key underneath, KEY, 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 on and on. Because 9 is exactly 3 times the period, the key has cycled all the way around, back to the very same starting position, by the time it reaches the second the. And that has a remarkable consequence. Encrypting THE with the key letters KEY gives the ciphertext DLC, but because both copies of THE sit under exactly the same 3 key letters, both produce exactly the same ciphertext, DLC. And the distance between those 2 DLCs is 9, exactly 3 times the period. Now run the logic backwards. Whenever you spot a trigram repeating the ciphertext, the distance between those repeats is almost certainly a multiple of the key length. That, in one sentence, is the whole trick. With the toy example out of the way, let us turn the same idea loose on a real ciphertext. 133 letters, freshly intercepted by our attacker. Step 1 is to scan the entire thing for any trigram that appears more than once. By hand this is tedious, but it is purely mechanical, and a computer will do it in a fraction of a second. And the scan turns up 2 repeats. IHV appears at position 0, and again at position 110. And TYM appears 3 times over, at positions 31, 46, and 61. Now for the part that actually matters. We measure the distance between every pair of matching trigrams. IHV gives us a single distance of 110. TYM gives us 3, 15, 15, and 30. and according to the Kasiski insight, every single one of these numbers should be a multiple of the keyword length. So to pin the keyword length down, we reach for the greatest common divisor, the biggest integer that divides every single distance with no remainder. 5 divides 110 22 times over, 5 divides 15 3 times, 5 divides 30 6 times, and no number larger than 5 divides all of them so cleanly, so the GCD is 5. And there it is, the keyword has 5 letters. We've not yet decrypted a single character of the message, but we have already shattered the central illusion of Vigenère. We know its period. Knowing the period, though, is only half the battle. The other half is putting it to work. To see how, take the first 20 letters of the intercepted ciphertext and lay them out in a single row. Because the keyword has length 5, every fifth letter shares the same key letter. All the letters painted the same color here were encrypted with one and the same shift. That means we can pull these letters apart into 5 columns, 1 column for each key letter. All the letters of one color go into column 1, all the letters of the next color into column 2, and so on for all 5. Let us now do exactly that for the entire ciphertext, all 133 letters. We will lay each column out as a horizontal row, so the whole picture fits comfortably on screen. And here is what the split buys us. Every letter in a single row was encrypted with the very same key letter, which means each row, taken on its own, is nothing more than a humble Caesar cipher. In other words, we have turned a single Vigenère cipher into 5 independent Caesar ciphers, and Caesar ciphers we already know how to break. Now, you might be thinking, why not just brute force it, the way we did with Caesar? Try all 26 shifts on each row, and pick whichever one looks like English. The problem is that each row is a scrambled fragment of the original message, not a readable sentence. Brute force worked on Caesar because we could eyeball the output for words. Here, no shift is going to give us recognizable English, only a jumble of the right letters in the wrong order. Frequency analysis, on the other hand, does not need whole words at all. It rests on the statistical distribution of individual letters, a property of the language itself, which survives regardless of word boundaries or letter order. So as long as the original message was English, the letter frequencies in each row will still follow the English pattern. Before we attack our first column, a quick refresher on how frequency analysis breaks a Caesar cipher in the first place. We worked through this in detail in the lesson on the mathematics of the Caesar cipher. Recall that in English, the letter E is by far the most common letter, accounting for roughly 12.7% of every text you will ever read. A Caesar cipher shifts the entire alphabet by a fixed amount, so the frequency peak moves with the shift, but it does not flatten or disappear. Which means the most common letter in the ciphertext is, almost certainly, the encryption of E. And once you know which ciphertext letter encodes E, the shift falls straight out. Subtract E's index from the peak's index, and what you are left with is the key letter. With that recipe in mind, let us start with column 4, because it gives us the cleanest result. Here are its 26 letters. Count up the letter frequencies, and one letter immediately dominates. M turns up 6 times, miles ahead of anything else in the column. So if M is the encryption of E, the shift is 12 minus 4, which is 8, and the 8th letter of the alphabet is I, which means column 4 hands us its key letter, I. Column 1, on the other hand, is trickier. Its frequency distribution has a tie right at the very top, and that means we're going to have to dig a little deeper to find the right shift. Column 1 has 27 letters. Count for frequencies, and we find 2 letters tied for first place at 5 appearances each, I and T. Here's the picture. I and T are neck and neck. When a top spot is tied like this, we have to look beyond just E and ask which other common English letters the rest of the distribution lines up with. Suppose first that ciphertext T is the encryption of E. That gives us a shift of 15, which corresponds to key letter P. Now, under the same shift, what does ciphertext I decrypt to? I minus 15 gives us T, and T happens to be the second most common letter in English, and sure enough, I also appears 5 times on our column. So the 2 most frequent ciphertext letters map cleanly onto the 2 most frequent English letters. That is a very strong signal. But to be sure, let us test the alternative. If ciphertext I were the encryption of E instead, the shift would be 4, giving key letter E. Under the shift, ciphertext T would decrypt to plaintext P, but P is barely 2% of English text. 5 occurrences of such a rare letter in only 27 samples would be extraordinarily unlikely, so the numbers comfortably rule the alternative out. And that settles it. Column 1's key letter is P. So far we have worked 2 columns in detail. Column 4 gave us the key letter I straight from its cleanest peak, and column 1 gave us P after we had to break a tie at the top of its frequency chart. The remaining 3 columns yield to exactly the same technique, so rather than labour through each one by hand, let us simply state the results. Column 2 is the cleanest of the lot. Its top letter is E itself, which means a shift of the 0 and a key letter of A. Columns 3 and 5 have messier frequency distributions, but the same checking which shift produces plausible English technique narrows each one down to a single answer. Column 3 resolves to R and column 5 resolves to S. And here is a picture all in one place, reading the key letters from top to bottom, P-A-R-I-S. The keyword, of course, is Paris. Now let us watch the entire crack play out from start to finish. We start where we started, 133 letters of intercepted ciphertext. Step 1. Hunt for repeated trigrams. I-H-V appears twice. And T-Y-M appears 3 times. The distances share a common factor of 5, so the key has length 5. Split the ciphertext into 5 rows, 1 for each position in the key. In each row, find the most common letter, the encryption of E, and subtract E from it. Out falls the key letter for that row. Read the 5 key letters down the side, and they spell Paris. Apply the key and decrypt every letter in place. Slide every letter back into its original position. And there it is, the message in the clear. Now that the dust has settled, let us step back and ask what really made this attack possible in the first place. The fatal weakness of Vigenère is repetition. The key word is shorter than the message, so sooner or later it has to cycle back to itself, and the moment it does, the cipher loses its polyalphabetic disguise. Repetition in the key creates repetition in the ciphertext, and that repetition is exactly what Babbage and Kasiski reached in and exploited. And notice that none of this is specific to Vigenère. Any polyalphabetic cipher that uses a short repeating key falls to exactly the same idea. The period always betrays the cipher. And the cure is simple to state, even if it is surprisingly difficult to achieve in practice. Never reuse the key. Make the key as long as the message itself, and choose every single letter of it completely at random. That cipher has a name. It is the Vernam cipher, also known as the one-time pad, and it is the only cipher that has ever been proven mathematically unbreakable, and that is where we are headed next. If you want the rest of this cryptography course, hit subscribe so YouTube tells you when the next lesson drops, and a like on the way out helps other learners find it.